Hello everyone, in this video I'll be discussing how matrices are used in neural networks and we'll make one in Rust. So let's get started. What is a neural network? So basically, it's something that's used in artificial intelligence, and that may seem daunting, but basically, it's like a brain. So we have what are called input neurons, right? And then we have what are called hidden layers. So these are the input neurons, and then we have some hidden layers. What are they called? Let's say that. So these are the hidden layers, and then we have some output neurons. And each of these neurons are connected like so. You can sort of imagine that just like they're connected to each other. And what's happening is we're giving the network these inputs, and then we want it to predict what the output is going to be. So let's say we're playing a Flappy Bird game, for instance, and we want to train the computer to play Flappy Bird. Well, one of these input neurons can be like how high the Flappy Bird is, how high you are off the ground. One of these can be how high the next pipe is, and one of these can be how far away from the pipe you are, right? So we're giving it information about the environment, and then what it's doing is it's doing some crazy math in the background with this hidden layer, and then it's spitting out some information into these output neurons. So input, hidden, output. And these outputs will say, oh, should we click or should we not click? Right? So how does this math work? Well, what's going on here is we give it these inputs, and then it uses something called weights to decide what the next layer is going to be, right? So let's say we give this one a value of 0.5. We put that into this input neuron. What it'll do is, for each of these neurons in the next layer, it will multiply that 0.5 by a weight, what we'll call W. And then each of these neurons has what's called a bias, like it's biased towards one value or another. So then we're going to take that 0.5, multiply it by the weight, and then add a bias. Right? Pretty straightforward. So for each of these like connections or links, whatever you want to call it, we want to multiply the input times the weight, and then add the bias to get the next neuron. And then this continues forward. This neuron is going to get multiplied by a weight and added to a bias to get this neuron. And then that neuron's going to be multiplied by a weight, add a bias, and it's going to give it this output. But the output neuron is actually the sum of all of these weights. So this neuron is taking all of these inputs, multiplying them by a weight, and then adding its bias. So you can think of it as we're going to add together the weight times the input, right? And then we're going to add a bias. And that's how we're going to get the next neuron. Right? So this seems very computationally intensive, right? And imagine you're doing this and you have to do that many calculations. You have to decide how many of these neurons we have to do. It's just very confusing, right? But there's an easier way around this. What if instead of thinking about each of the neurons individually, we use matrices? So let's go from one layer to another. We can think of this layer as just a matrix, right? So instead of thinking of this as 0.5 and like this one as 0.2, we instead think of this as a matrix of 0.5 and 0.2, right? So that is this layer. And then what we're going to do is we're going to multiply by some weights. Now this is a 2x1 matrix, right? 2 rows, 1 column. So that means we have to have a, wait. So we have a 2x1 matrix. What we're going to do is we're going to transpose this matrix, which sort of means like, we're going to make all the rows into columns. It's kind of confusing, but we're going to take that matrix and we're going to transpose it. So, So we're going to take this matrix and we're going to turn it into this. As you can see, all the rows become the columns, right? We're sort of just like turning it, or I don't know how you describe it, but you would turn all the rows into columns, and then now we have a 1 by 2 matrix, right? So we can multiply this by a 2 by 3 matrix, right? 2 rows by 3 columns. So let's say we have A, B, C, D, E, F, right? And this is what's going to be our weight matrix, right? So this is our input matrix, this is our weight matrix, and then that will give us a resulting 1 by 3 matrix, right? And it's going to give us some 1 by 3 matrix. And what's nice about this is, this might seem kind of random, but what you'll see is we're multiplying this input value by A, and then adding that to this input value times D, right? So it's going to be 0.5 times A plus 0.2 times D. And then that's going to give us this neuron right here. Now, look at that. We have 0.5 as the input times A, where A is the weight of this connection, and then 0.2 times D, where D is the weight of this connection. We basically just did all of that math for one neuron, and we just had to multiply these matrices. But it gets even better, because this next column, B and E, that's going to be the weight of this connection, and it's going to be the weight of this connection, right? It's going to be 0.5 times B plus 0.2 times E, and that's going to give us this neuron. And then the last one, C and F, right? We have this connection is C, this connection is F, 0.5 times C plus 0.2 times F, that's going to give us this neuron. So this resulting matrix, this matrix that we just got here, that's actually just all of this math done in one simple calculation. Just multiplying two matrices. And if you don't know what matrix multiplication is, I recommend reading up about that, because this might be kind of confusing. But we're going to multiply these two matrices, and then the resulting matrix is going to be our next layer of neurons. Now we can just continue off of that. Let's say we have two more neurons over here. We can take this matrix, which is a 1 by 3 matrix, right? And then we're going to multiply by some sort of a 3 by 2 matrix, right? So we have 1, 2, 3, 1, 2, 3, and these are going to be random values, right? But what we're going to do is we're going to say 1 times 3, and then we're going to multiply that matrix by a 3 by 2, which will give us a resulting 1 by 2 matrix, right? And you'll see this is a 2 neuron layer, right? So after multiplying by this matrix, we will get a 2 neuron layer that's going to be the weights of all of these. And the final step, after we've done all of that weight calculation, is we can add the bias, and that's super easy too. We can have a bias matrix, which is going to be like a 1 by whatever the size of the layer is. It's going to be a 1 by A matrix, and then this matrix is going to have some values inside. And then what we can just do is just add these two matrices, right? So XYZ plus this, that's going to add all of the biases in one simple calculation, right? So to get from one layer to the next, instead of having to do thousands of calculations to get all of these weights, all of these biases, we only need to do two calculations. One is a matrix multiplication, and one is a bias addition. So that's what's called forward propagation. We're going to do this for each layer. We're going to get this matrix, multiply by the weights, add the biases, get the next layer. Then we're going to say that layer is our current layer, multiply by the weights, add the biases, and then we're going to get the last layer. So that just sped up our calculations by a lot, right? It's a lot more easy to understand than having to do all of the calculations one by one. Now, that's good and all, but you might have realized I said before, the matrices are random, right? we start off with a random matrix, and it's just going to be random values like 0.1, 0.2, 0.0, negative 0.5 or something, right? It's going to be a random matrix. Now, how are we going to reverse this, right? How do we know whether or not our answer is right, and how do we tune our neural network to produce the right answers given the inputs, right? That's where something called back propagation comes into play. So we have forward propagation, which is sort of like going through all of these weights and biases, and then we're going to go forward, right? Or feed forward, right? We're going to feed the inputs forward, and then we're going to have back propagation, which is starting from the outputs. We're going to find the errors between that and what we expect the outputs to be. We're going to find the difference or the errors, and then we're going to map them to a gradient, right? And this is called gradient descent. So we're going to map them to a gradient, and then what we're going to do is we're going to basically reverse the matrix calculations to go back, right? We're going to go back here. We're going to come to these layers, and then we have the errors for these layers. So for instance, if we know that this neuron is always giving a faulty answer, that neuron will have a greater error than these ones. So we can say, oh, that neuron has a greater error. We either modify the weights or we modify the biases, right? And then we go back one more layer. We just keep on going back, and then until we get to the end, and then all of our errors are just slightly better, right? We're gonna have a slightly better neural network than we did before, and that's the basis of machine learning. We're just gonna learn. We're gonna learn for like thousands of times, and just by these small tweaks that we know because we have these errors down here, and we're gonna find which neurons are responsible for the error. We're gonna find how to fix those errors, and then we're gonna go back. It's like a small child learning how to walk, right? Through these small errors, the neural network is gonna learn what the right answer is. And that's really cool. So, how do we do this? Well, what I'm gonna do is I'm gonna open up a terminal, and then you can use any code editor of your choice. I'm gonna use NeoVim, and then I'm just gonna open up my project right now. Alright, so when you get to a directory that you want to use, you're gonna say pogo init dot, and then that will just make a new Rust project for you. I've already started this one, so we don't need to waste time downloading on the packages and stuff. But as you can see, we only need one dependency, and that's going to be the random package. And this is just going to be for randomizing our matrices in the beginning. So we're using random version 0.5, and then yeah. So open up that directory in your favorite text editor, and then we can get to coding. So first off, we need a lot of matrix math, right? We can't really do this if we don't have a matrix, right? So what we're gonna do is I'm gonna go into source, and then I'm gonna make a new file in the lib directory called matrix.rs. Right, so we're gonna have a lib folder, and we're gonna have a matrix.rs file. Now, we're gonna have a struct called a matrix, and then we're gonna use that matrix struct to do some cool math. So let's say pub struct matrix, and then we're gonna say pub rows, which is gonna be a usize. Pub columns is gonna be a usize, and then we're gonna have pub data, which is gonna be a vector of a vector of float 64s. So basically we have a matrix, right? And this is gonna store three different things. It's gonna store the number of rows it has, it's gonna store the number of columns it has, and it's gonna store the data, which is gonna be a vector of float 64s. Now, vector in Rust, not to be confused with a vector in math, which is sort of like a line or whatever. Vector is just like an array. like a list of items. And then we can go down here and say, we're gonna implement some traits for a matrix. So, well, first off, we're gonna have a method to get the zeros of the matrix. So we'll say pub function zeros, and then we're gonna take rows, which is gonna be usize, and columns, which is gonna be a usize. And then the return value is gonna be of type matrix. So we're gonna give a matrix of rows, columns, and then we're gonna have data, which is gonna be a vector filled with zeros of size rows, of size columns, and of size rows. So this is just shorthand in Rust for making a vector, and this vector is gonna be filled. It's gonna be a vector of size rows filled with vectors of size columns filled with zeros. So you can sort of imagine we're going to have just like a 2D array. We're going to have a 2D array, and it's going to be of size rows, and it's going to be of size columns, and then it's just going to be filled with zeros, right? This is basically what that is doing. And then we're going to also need to have a random matrix. And this is just going to be for our weights and stuff. So we're going to say public function random. We're going to take in rows, which is going to be usize, columns, usize, and then we're going to output a matrix. And then this is going to be a matrix of rows. It's going to be data. Oh, wait, no. Sorry. We're going to have to use a random library. So let it's going to be a mutable variable. Let be rng equals thread rng. I'm not getting autocomplete. Oh wait, sorry. So since we made this matrix in a library in the lib directory, we're gonna actually have to include it in the module tree. So we're gonna go to source lib, and then we're going to create a mod.os file, and then we're going to say, in mod.os, we're going to say public module matrix. And again, in the source file, in the main.os, we're going to say pub mod lib. And this is basically just going to import all of this into here. Oh wait, and these need to be semicolons. Right. So now we have our file included in a module tree. We can actually do some stuff. So we're gonna thread rng using the random library, and this is just gonna give us some random values that we can use, and then we can say let mutable result equals matrix zeros. So we're going to make a matrix of zeros, and they're going to be rows by columns, right? And then afterwards, we can use a nested loop. So for I in 0 to rows, for j in 0 to columns, we're going to say res.data of I j equals rng generate float 64s, and then we're gonna multiply by 2 and then subtract 1. Now basically what this is doing is rng gen is gonna give us a random float between 0 and 1, right? So if the random float is between 0 and 1, and we multiply that by 2, that's going to give us a random float between 0 and 2, as you can imagine. So now that we have 0 and 2, we can subtract 1, and that gives us a random float between -1 and 1, right? So might be kind of confusing, but this ONG gen, that's basically just giving a random value between -1 and 1 for each of our data entries. Oh, we need to import thread ONG from our RAN library. No method name, gen. What? Oh wait, it's not thread ONG, it is just ONG. There we go. And then now, after we do a nested loop, we can just return res. So basically, we're making a matrix of zeros of size rows and columns, and then for every element, we're going to generate a random value between -1 and 1, and we're going to set it to that value. Alright, and then one of our last helper functions is going to be public function from. Now from is going to basically take a vector. Actually, no. Let's not do this right now. That might not actually be even useful. So yeah, so we have these two functions that let us create a matrix. Now we get to actually make the math part, which is going to be interesting. So matrix multiplication. Public function multiply by a, so we're going to need our immutable self, and then we're going to need the other, which is going to be a borrow of a matrix. And then it's going to output a matrix. What we're going to do is, first off, we need to check if this is even possible. So if self.columns is not equal to other.rows, we can panic, which is basically to say we're going to error, and we're going to say panic that attempted to multiply by matrix of incorrect dimensions. And then this is just checking if our matrix multiplication is even possible. So given that our multiplication is possible, we're going to say let mutable res equals matrix of zeros of self.rows and then other.columns. So if you know about like matrix multiplication, basically we have a matrix. Let's say we have a matrix of size. This is going to be a matrix A of size like A by B, and then we're going to multiply by a matrix B of size C by D. This is going to be a matrix of size C of A and D. Right, so it's going to be of size A's rows, and it's going to be of size B's columns. Right. So we're going to have let mut res equals matrix 0 self.rows other.columns, and then for I in 0 to self.rows, it's just another loop. So for j in 0 to in other.columns, right, so we're basically going to go through each of the rows of this one, and then each of the columns of this one, and then we're just going to multiply them. And then how we're going to do that is, we're going to get a sum, so let mut sum equals 0, and then for k in 0 to self.columns, we're going to say sum plus equals self.data of I k times other.data of kj. Now this might be a little bit confusing, but I'll explain it in a second. So res.data I j equals sum, and then we're just gonna say return res. Right, so matrix multiplication. What we're gonna do is we're gonna take the first. So let's say we're gonna look at the first row of A. Right, we're gonna take a look at this first row of A, and then we're gonna take a look at this first row of B, and then we're gonna multiply these two rows, and that's gonna give us this value here at 0, 0, right? So the 0th row of A, 0th row of B, that's going to give us index 0, 0. Now, how does that work? So we have A, right? We're going to take the first element of A's row and multiply by the first element of B's column. Then we're going to take the second element of A's row and multiply by the second element of B's column. Third element of A's row, third element of B's column. Multiply those, and then we're going to add all of those together. Right? We're going to add the first elements, the second elements, the third elements. We're going to add the products together. And then the sum of all of those is going to be this value right here. And what this is basically doing is we're getting the ith row of this original matrix. We're going to get the jth column of the other matrix, and then k is just going to be constantly incrementing. Like k is just going to be going up by 1. So we're going to have the ith row of our self of index k times the jth value of the other column index k is going to get multiplied together and added to the sum, right? So k is going to be increasing by 1. We're basically just going to be going 1, 2, 3, 4, and then like 1, 2, 3, 4, and then we're just going to multiply them together and then add them to sum. Hope you understood that. And then we're going to have public function add, which is also going to get mute self. Other, which is going to be a borrowed matrix, which is going to be a type matrix. And then if self.rows is not equal to other dot rows, or self.columns columns is not equal to other dot columns, we're gonna panic, saying you're attempting to multiply by matrix. No, not multiply. Add matrix of incorrect dimensions. Oh wait. Oh, got a colon here. So add is going to be a lot more straightforward, since we're basically just going to go through each individual element of both matrices, and we're just going to add them and then put them into the resulting matrix. So, and this is just to check to see if the number of rows is the same and the number of columns is the same, because if they're not the same size, then we can't add them. So let mute res equals matrix of matrix zeros of self.rows, self.columns, right? And then we're going to say for I and 0 to self.rows, for j and 0 to self.columns, we're going to say res.data of I j, of ij equals self.data of I j plus other.data of I j. And then we're going to just return res. So again, we're just going to go through every individual element of self and every individual element of other, add them together, and set them to the resulting matrix. Pretty straightforward. Oh gosh. Public function dot multiply, which is going to have a mute self, and then other matrix. Now, this is going to be, actually wait, hold on. This isn't really dot multiply. This is more of it like, just going to be like, what are we going to call this? I think it's called dot multiplication. We're going to call it dot multiplication. So basically, instead of multiplying these matrices like we did with the original matrix multiplication, we're going to basically do what we did with addition, right? So we're going to have like this. We're going to dot multiply by bam, 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 bam. So the resulting matrix is just going to be this times this times this, right? So we're just going to go through every individual element and multiply them. It's like a less complicated matrix multiplication. And in that case, we can actually just copy this basically, and then just change this to a multiply. Pretty straightforward. And then we're going to say attempted to dot multiply by matrix of instruct dimensions. There we go. Oh wait, we need to return a matrix. That's right. Alright. So we have that, and then we're gonna also need a subtract method, which is kind of maybe a little too redundant, but it's nice to have because we're gonna use it later. So, and again, we can basically just copy this add, and then we're just going to change this addition to a subtraction. So we're basically just getting the whole family of matrix operations in here. Alright. Final two. Public function map. And then this is basically just going to map a function onto every individual element of the matrix. So we're going to take a function, and this is going to be a dynamic function, which is going to take a float 64 as an input, and then it's going to output a float 64, and this whole function is going to output a matrix. So basically this just means that we're going to get a function, we're going to have like a dynamic function, if you will, that's going to take in a float 64 and then return a float 64. So we can say let's mute res. Again, it's going to be a matrix of zeros of self.rows and self.columns, and then for I in 0 to self.rows, for j in 0 to self.columns, we'll just say res.data of oh wait, this is the wrong thing. Never mind. map is gonna be something different. Map is it's gonna be a matrix that's gonna be from. Oh wait, hold on. So, what map is gonna do? Please stop. I should explain this real quick before I started screwing around with some stuff. But map is basically we're just gonna take every individual element, and then we're going to apply it to a function, right? So let's say that f of x equals like let's just say something simple, like x plus 1, right? So what we're going to do is we're going to say, for each of these elements, we're going to put that into the function and then get the result, and then put that back in the position, right? So map is just going to take a function, and then it's going to, for each of the elements in the matrix, use that function to map onto the element, if you will. So we're going to say matrix.fun, but first off, we need the fun function. So this is going to be a super simple function, but basically we need a way to go from a vector array, a 2D vector to a matrix. So we're going to say from data, which is going to be a vector of f64s. And then this is going to give us a matrix. And then simply, we're going to say matrix of size rows, data dot length, columns, data, the first row of data dot length, and then we're going to say data. Pretty simple. Oh yeah, so that's good. So we can go down here, and then we're going to say matrix.from self.data, parentheses, dot clone, right? So we're going to clone our data, and then we're going to turn that into an iterator. Now, it's important to clone the data because otherwise, in Rust, you're going to have you're gonna have a random ball that's not supposed to happen. So we need to make sure to clone it, and then we're gonna turn it into an iterator. And then in that iterator, we're gonna map for each element, for each row, we're gonna say row.intoIter dot map for each value. So we're just gonna iterate through every row and every value, and then we're gonna say function of value. Right, so we're gonna call the function of that value, and that's gonna return a value that we're gonna end up putting into everything. So then we're gonna collect all of that, and then we're gonna collect all the rows. Type annotations needed. Oh, into. So basically, what we're gonna do is we're gonna clone our data, we're gonna turn it into an iterator, and for each element of that iterator, which is gonna be a row, right? So for each row of the matrix, we're gonna map for each value, right? We'll call the function of the value, and then we're gonna collect that iterator back into an array. And then that's gonna be how we get our data back. And then finally, public function transpose, which is gonna be mute self. This is gonna be our matrix transposition, right? So what I said before, we're gonna basically turn all the columns into rows and all the rows into columns. So let mute res equals matrix of zeros of self.columns self.rows, right? So we're gonna basically think of it as like reflecting over the y equals x line, if you will. We're just gonna sort of like turn the matrix on its side. For I in 0 in self.rows, for j in 0 to self.columns, we're gonna say res.data of ji equals self.data of ij. So we're gonna take all the elements, and we're basically gonna say, like for instance, this element right here, right? It's in the 0th row, and it's in the second column, right? So 0, 1, 2, right? This is gonna be the 0th row, second column. The transposition of this value is gonna be in row 2, column 0. So we're gonna basically just swap it over here. And then this one is gonna be, like for example, 1, comma 2. So that's gonna turn into 2, comma 1. So you can still, actually it's not the y equals x. You can sort of think of it as reflecting over the y equals negative x line, right? So all of these elements are gonna sort of get like turned over that line. Alright, and one final thing is up here in our struct declaration, we might need to clone this later. So we're gonna derive from the clone trait, just so we can clone this matrix if we need to. Alright, that's it for our matrix class. So now we can actually get started with our network. Let's make a new file. In our lib directory, we're gonna call it network.os, and let's open that real quick, and let's get started with our network. So again, we're gonna have oh wait, hold on. Before we forget, we should add this to our mod file. So public mod network. So now that that's included in our file directory, you can say public struct network. And then we're going to say layers, which is going to be a vector of usize, weights, which is going to be a vector of matrices, biases, which is going to be another vector of matrices, and then we're going to have data, which is going to be another vector of matrices. Alright, yeah, that should be good for now. So we can say implement some traits for network. Alright, so we're gonna say public function new, and this is gonna be how we're gonna create a new network. We're gonna have a layers, which is gonna be a vector of usizes. So what I'm talking about with layers here, I don't mean the actual layers. I mean we're gonna pass in an argument, which is going to be how big the layers in the matrix is going to be, right? So so let's say we want our network to look something like this, right? So it's going to be 2, 3, 2, 2. Our layers vector is going to be just this, right? So it's going to be a list of the sizes. The list of the sizes of each of these matrices, right? So that's basically what our layers is going to be. It's going to be a vector of u sizes, and then we're going to have, yeah, that should be all actually. And then, oh wait, this is going to return a network. So we're going to have let mute weights. It's going to be a vector, an empty vector for now. Let mute biases is going to also be an empty vector. And then for I in 0 to layers.length minus 1, because like let's say we have, this is 4 layers, right? We're only going to have 1, 2, 3 weights, right? 3 layers of weights. That's why we're going to subtract 1 from layers.length. Weights dot push, it's going to be a matrix random. We're going to randomize a matrix of size layers I plus 1, and then layers I. So basically what we're going to do is, this layer is of size 2, this layer is of size 3, so we're going to make a matrix of size 3 by 2, right? So when we end up multiplying this matrix in front of the other matrix, we're going to get this 3, right? Yeah. And then we're going to say biases.push matrix random of layers I plus 1 and then 1. Oh gosh. Excellent network. Trying to find biases. My spelling is absolutely terrible right now. I saw the same thing. Biases. Oh wait, and we need to import matrix too. So let's quickly import that. Oh yeah. And then what we're going to do is we're going to return a network of size layers with the weights, with the biases, and with the data, which is, for now, it's going to be an empty vector. Now, data is going to be important later when we do backpropagation, which is going to basically tell us, oh, what are the errors that we have? And then we can go down here, public function feed forward, and we're going to take a mutable self, and then inputs, which is going to be a vector of F64s. And then this is going to output a vector of F64s. So basically our input is going to be a vector right here, so it's going to be something like it's going to be something like 0.5, 0.2, 0.5, right? That's going to be our input, and then the feed forward is going to give us an output, and that output is going to be something like 0.1, negative 0.3, or whatever, right? So let's get started with feed forward. This is pretty simple. So if inputs.length is not equal to self.layers 0, and basically that means that if we don't get the right amount of inputs, we're going to say panic invalid number of inputs. Now we're going to say let mute current. Now current is going to always keep track of our current layer. So equals matrix from, it's going to be a vector of inputs, and then we're going to transpose this. Because again, if we start off with a vector of something like 0.5, 0.2, we need to transpose that into this, right? 0.5, 0.2, right? We need to sort of flip it on its side. And then we're gonna say self.data equals a vector of current.clone. So basically, we're gonna say we're gonna keep track of the values that are stored in these datas, right? So we're gonna say vector of current.clone. We're basically just gonna clone this matrix and then store it as one of our data entries, just so we have stuff that we can rely on. This is sort of like that guy Blah. If you take an APO, he kept track of the celestial bodies for like 20 years. He kept data on all of them, and that helped all of the astronomers to know where the planets were going to move. This is sort of the same thing. We're just basically storing a vector of the data points, just to keep track of everything. And then we're going to say for I in 0 to self.layers.length minus 1, because again, we only have length minus 1 number of layers. We're going to say current for self.weights at index I dot multiply by current, and then we're going to dot add self.biases of I. And then, okay, so I kind of left something out in the beginning when I was talking about feeding forward. We have something called an activation function, right? Because without an activation function, what's going to happen is some of the values might get too out of control, right? And what an activation function does is it sort of tones down the values. So, for example, one of the most popular activation functions is what's called a sigmoid function, right? And it looks something like this. And then, the sigmoid function, what we're going to use for it is actually just 1 over, 1 plus e to the, negative x, right? And that's going to give us a graph of something that looks sort of similar to this, right? And then this line right here, it approaches 1. So as you can see, it's sort of like this gradual slope up, right? But whatever input we give, right, whatever x is, it's always going to be between 0 and 1. Right? It's always going to be between 0 and 1. And this just makes sure that all of our values stay within, like, a set boundary, which is going to be super helpful later. So to add self.biases 1, index I, and then we're going to map with a, self.activation.function. Yeah, let's do the activation functions right now, because we're on this right now. So we're going to create an activation file, activations.ls, and then this gets a little bit tricky in terms of Rust, but basically we're going to have, we're going to need a derive from clone. So we're going to have a public struct activation, and this is going to store both the function itself and its derivative, which I'll get into later. But basically we're going to have an activation, and because we're going to be inputting this later, we need to specify a lifetime. So we're going to have a lifetime of a, and then public function, we're just going to use the lifetime specifier. It's going to be a dynamic function of 64, f64, float 64, and it's going to output a f64 as well. And then same goes for its derivative. Now, what the derivative is, right, it's going to be, it's sort of going to be like, if this is like y equals this, we're going to basically put x equals 1 over 1 plus e to the negative y. We're going to sort of like swap e and y, and then x and y, and then we're going to solve for y, right? And then this is really complicated to solve in like calculus and stuff, so we're going to use a simpler function, which is just going to be it's just going to be x times 1 minus x, right? Oh, let's be x times 1 minus x, right? That's going to be like a simplified derivative of that function. And what the derivative is going to do is, remember how I said in backpropagation, we need to like undo all the steps? It's sort of like unraveling all of our errors, right? If we mapped an activation function on a value, we need to also map a derivative when we're going backwards so that we get the old value back, right? We need to know what the old value was when we're going backwards. Oh, and I forgot an F and I need to include some model tree. So, public module activations. Right. So you can make a lot of activation functions. I'm just gonna make a simple one called sigmoid right now. So we're gonna make the sigmoid activation, which is gonna be an activation, and the function is, again, it's gonna be we're gonna take the x value, and then we're gonna say 1 over 1 plus e, and e is just like a default constant in Rust, dot power a float to the negative x. And I forgot, I don't think e is actually a constant, and we need to import it. So use standard library f64 constants e, and e is just Euler's number. It's like, I think it's like 2 point something, 2.6. And then we're gonna have a derivative. We're just gonna take the x value, and then we're just gonna say x times 1 minus x. So just a basic derivative. And then now we can actually have an activation function on a neural network, which is pretty nice. So we're gonna come up here, and then now we need the activation function. So we're gonna say activation, and it's gonna be of type activation. But remember, again, we need the lifetime specifier, which also means we need a lifetime specifier for the neural network, which means in a new network implementation, we also need a lifetime specifier. So right here, and then so new, we're gonna have the same lifetime specifier, and then we're gonna take in an activation, and then now we can use this activation lifetime specifier to know when we need to like delete that memory. And then down here we can just say activation, right? And don't worry if you're kind of confused about the lifetime specifier. I was kind of confused by it too, but it sort of just means like when we should remove this from memory, when we're not going to use it anymore. So we're gonna say current equals self.weights.multiply.add.map, and then we're gonna say current.data 0.2, no, not that, self.data.push current.clone. Right, so again, we're just we're gonna clone this just so we have it on record so we can use it later. And then we're gonna say current.data index 0.2 owned. Right, so what we're gonna do is we're gonna say in our neural network, right, this is our current layer right now. Right, this layer is gonna be our current layer right now. We're gonna multiply away weights, we're gonna add the biases, and then we're gonna map an activation function. And then now this is gonna be our current. We're gonna multiply weights, add the biases, map the activation. This is gonna be our current, and then once we reach the end, we just clone it and then we give it back, so we know what the result is. Nice. And then Okay, this is where it gets kind of difficult. The backpropagation. It's not a lot of code, but it's kind of difficult to understand. So we're going to say public function backpropagate, and then we're going to take a mutable self outputs, which is going to be a vector of f64s, and targets, which is going to be a vector of f64s. And then what's going to happen is we're going to say if targets.length. So targets is just like, how do I describe this? So let's say we're using this network to predict handwritten digits, right? If I write like a 1 or if I write like a 2 or something, I want the network to be able to predict that. So let's say the output, we have like one output neuron, and then now output neuron goes from 0 to 1, and then it's going to say like 0 to 0.1 for 1, 0.1 to 0.2 for 2, right? So it's going to give us a prediction of what the answer is, right? But we need to tell it if it's right or wrong, right? So we're going to say that, oh, I drew this, but you thought that was a 3, right? You thought that was a 3, so you output is 0.3, but it was actually a 2. So our target is going to be 0.2, and then using that, we can calculate the error, which is 0.1. And then we can use that error to find a gradient, like to do gradient descent. Right? So targets.length is not equal to self.layers of self.layers.length minus 1. So just the last element of self.layers. If we don't have the right number of targets, we're going to panic, saying invalid number of targets. And then we're going to say let mute post equals matrix from vec of outputs, and then let mutable errors equals matrix from vec of targets dot subtract post. Right. So we're gonna post the outputs into a matrix, and then we're gonna subtract it from the targets, and that's gonna give us the errors, right? So by doing matrix subtraction, we can get the difference between each individual output neuron, and that's going to tell us, oh, we need to fix this, we need to fix this, we need to fix this, right? And then we're going to have let mute gradients. That's going to be the error gradients, and that's going to be post.map of self.activation.derivative. And again, we're just sort of undoing the activation function we applied earlier with its derivative. So for I in 0 to self.layers.length minus 1, and then since we have this iterator, we're actually just gonna reverse it, because instead of going forward, we're going backwards now. So we're gonna go from 0 all the way to like the length, but we're gonna reverse it. So instead of going layer 0, layer 1, layer 2, layer 3, we're gonna go layer 3, layer 2, layer 2, layer 1, layer 0. And then for when we're going backwards, we're going to say gradients equals gradients dot multiply by the errors, right? Because, so we're going to multiply by the errors, right? And that's going to give us sort of, that's going to tell us what we did wrong, basically. And then we're going to map, okay. So we're going to map x times self.learning rate. Now, this is something else I forgot to mention, but basically, neural networks, they have something what's called learning rate, which is kind of optional, but it's really nice if you have it. And this is just going to be a constant, right? It's going to say how much do we want to tweak the neurons by, right? Do we want to tweak these weights by a lot each time, or do we want to do it a little each time, right? And when you're training neural networks, you kind of want to find the sweet spot, right? Because if you tweak it too much, it's like, it'll be like a pendulum, right? If you tweak it too much, and the pendulum has too much energy, it's just gonna swing right past the middle, right? But if you do it too little, then it's gonna take a long time to actually reach the desired output, right? So you want a good loading rate, and then I'll talk about that in a second. But how do we actually get this loading rate? Well, we need to get it from up here. So we also need a loading rate field, which is going to be a float 64, and then down here we also need a loading rate. So yeah, so that's just gonna be a field on our struct, and then it's gonna tell us how fast we want to load. So then we can say self.weights of index I equals self.weights of index I dot transpose dot multiply by the arrows. So what's happening here is we're gonna say for that weight of that layer, oh wait, hold on, no, that's wrong. We're gonna say self.weights of index I equals self.weights of index I dot add. We need to add the gradients, I believe, and then dot multiply we need to borrow the self.data of index I dot transpose. So what's going on here is we're going to take the arrow gradients, right? And then we're going to multiply them by self.data. And remember, self.data is keeping track of what we did before, right? It's keeping track of all of our data from each layer, right? And then if we multiply the gradient arrows by that, we can see exactly what we did wrong, right? We can see the difference between what was expected and what was actually produced, right? And then we're just gonna add that, because by adding it, we're just gonna tweak those weights by a little bit. And then we're gonna say self.biases of index I equals self.biases of index I dot map, no, dot add gradients. Now, since we used addition, we can actually just subtract the gradients directly from the self.biases. And I spelled biases wrong. Alright, and then finally we would just say arrows equals self.weights I dot transpose dot multiply by the arrows. And then gradients equals self.data index I dot map self dot activation dot derivative. So yeah. So basically what's happening here is we're gonna say the arrows is gonna be our current weights. We're gonna transpose them, and then we're gonna multiply them by the arrows, right? So we're gonna see the current weights, and then we're gonna multiply them by the arrows, right? So we're gonna get these weights right here. We're gonna multiply them by the arrows so we can know what went wrong with these weights, and then the gradients are gonna be self.data I dot map self.activation dot derivative, right? So these gradients are gonna basically say we're gonna map the derivative on them, and that's gonna just reverse the activation we did earlier, right? So what I was talking about with the sigmoid function, we're just gonna undo that, and that's actually all for backpropagation. It's kind of confusing, but basically we're just going through and finding the errors. And then we're going to use this gradient matrix to know what we did wrong, and then we're going to slightly tweak the weights to get a better result next time. Right? And then, yeah, that's the basis of a neural network. I'm gonna go to the top here because I spelled loading way wrong. Right. But something that'll make this easier to train is if you actually add a train function. So public function train. This is going to take a mutable self, so take an input, which is going to be a vector of f64. It's going to take a targets, which is going to be a vector of f64. No, vector of f64. And it's going to take an epochs. So epochs is just going to be how many times do we want to like cycle through these targets, right? And then what we're gonna do is for I in 1, 2 epochs, right? And what I like to do is I like to print out by percent, right? So you can say like if epochs is less than 100, because you can't really have percents if it's less than 100, or I modulus epochs over 100 equals 0. We're gonna say print ln epoch something of something, and that something is gonna be I of epochs. So this is going to give us like a nice printout saying what we're on right now, so we know that we're actually, we know how far we've already trained. And then we're going to say, for j in 0 in inputs.length, let outputs equal self.feed forward. We're going to feed the inputs of index j dot clone, and then what did I do here? Let outputs, and then we're gonna say self dot backpropagate. We're gonna backpropagate the outputs. We're gonna backpropagate the targets of j, and then we're gonna clone that. Right. Oh wait, no. This print C's as well. We're gonna clone the targets. Alright, so that's it for the neural network. Basically, the training function, what it's doing is, let's say we have like 1,000 epochs, right? It's gonna, for 1,000 times, it's gonna loop through all the inputs, loop through all the outputs, and then tell the neural network to feed forward the inputs, and then backpropagate based on the outputs. Right, so it's just going to speed up our training by a little bit. And now comes the fun part. We actually get to use our neural network. Which, it's been a journey. So, first off, let's create a new neural network. So let network equals network. We're going to import that. New. And what do we need right here? Feed layers. What are we thinking? I kind of want to make a network to predict an XOR, right? So if you know what XOR is, it's exclusive OR. It's basically saying if we have 0 and 0, we're going to output 0. If we have 0 and 1, we're going to output 1. If we have 1 and 0, we're going to output 1. And if we have 1 and 1, it's going to output 1. 1 second. Alright, so basically what's going to happen is we have 0, 0, it's going to be 0, 0, 1 is going to be 1, 1, 0 is going to be 1, 1, 1 is going to, actually this is going to be 0. So it's basically like an OR, right? It's sort of like an OR. But if they're both 1s, we're gonna say it's gonna be 0, right? So it's basically saying if either one of the inputs, if only one of the inputs is 1, we're gonna output 1. But if they're both 0 or they're both 1, we're gonna output 0. That's what XOR is, exclusive OR. So we're gonna have 2, 3, 1, right? We're gonna have a network of size, we're gonna have a network of size 2, 3, 1, right? And then the two inputs, that's gonna be like 1, 1, for example, right? This is gonna be a hidden layer, just a simple 1-layer neural network, and an output layer is gonna give us either 0 or 1, right? And then we're gonna train it. We're gonna say 2, 3, 1. Let's set the loading rate to like 0.5. I think that's about a good loading rate. And then we need an activation, which is gonna discrete sigmoid. Oh yeah, we need to make this a vector. Okay. So now we have a network. We need our data, right? And our data is actually gonna be really simple. So for inputs, we're gonna say let inputs equals a vector that's gonna have vectors inside. So we'll have 0, 0, 0, like 0.1, 0.0, 0.01, 1.0, and then this, and then I'll just move this up here. So it's sort of like what we have up here: 0, 0, 0, 1, 1, 1, 0, and then 1, 1, right? That's going to be our inputs, and then we're going to say let outputs equals a vector, and then this is just going to be a vector of just 0.0, 1.0, 1.0, 0.0. Okay, yeah. Right, so the inputs are going to be 0, 0, 0, 1, 1, 0, 0, 0, no, 1, 0, 1, 1, and then these are the outputs, right? So every element of the inputs has an output as well. And then now the fun part begins. We're going to say network.train, right? We're going to train it with, I think we need inputs, targets, and epochs. Oh, we should rename this to targets. Right, we'll train it with inputs, targets, and then epochs. Let's say like 10,000, because why not? And then now that we finally trained the network, we can say something like println. Let's predict what should we predict? Let's say 0 and 0. What is that gonna give us? Let's say feed forward, and we're gonna feed forward a vector of 0.0 and 0.0. Vector. Oh, we need to prettify this. Oh yeah. So let's just print out what it's gonna predict for each one. So 0 and 1, 1 and 0, 1 and 1. Network.feed forward 1, 0, 0, 0, 1, 0, 0, 1. Okay. Alright, the moment of truth. Let's see what this does. Ew, hold on. So expected matrix transpose. Oh, we forgot to return something. So down here we need to return was. Alright. Cannot borrow network as immutable. Oh, we need to make this a mutable network. Alright. Wait, hold on. I forgot to I forgot to print line here. So basically in Rust, print will not add a new line, so it'll just make a huge pile. We will see it's training for the epochs. And there we go. So 0 and 0 is gonna give us, it's almost 0, it's 0.01, right? So super close to 0. 0 and 1 gives us 0.98. 1 and 0 gives us 0.98. And 1 and 1 gives us 0.01. So, as you can see, our network originally, right, I can actually show you this real quick. Right, I can actually, show you what this is. So, before we train this, right, so, before we train the neural network, let's print the same things. Oh wait, hold on. I should probably do this outside. Hold on. Okay. So as you can see, before we actually trained the neural network, it thought 0 and 0 was 0.36, which I guess is slightly closer to 0, but this is still like terrible. 0, 1, 0.35, 0.41, these are just terrible answers, right? But after training it 10,000 times, you can see this neural network, look at this, 0.0002, that is super close to 0. Right, so this shows us that, this proves that the neural network is actually learning, right? Now, given this is simple, but this can actually be expanded to be used on different things. Like what I said, one of my favorite projects I did a couple of years ago was training neural networks to recognize handwritten digits, right? And that's like a super fun project because what you can do is you can break down the digits into pixels, right? And you can pass those pixels into the matrices, and then it'll do all that matrix math super fast, and then it'll give you a prediction on what number you wrote. Right? So it's just a super fun way to learn how to do neural networks, and that's about it for this video. I'll leave a link in the description if you want to check out this repository, and even if you want to just clone it and then run it on your own, or just screw around with it, play around, you know. But that's about it for this video. If you enjoyed, leave a thumbs up, and then leave any comments. I'm sure there will be a lot of questions, but I'll be happy to answer them in the comment section below. Alright, have a nice day, and thanks for watching.